So Coulomb's law gives the force on a charge due to any other charge. But if you have multiple charges present, then the net force on any one of them will be the vector sum of the Coulomb force between that charge and each of the other charges. Since force is a vector, you have to do vector addition, not just regular addition. So example 14.4 is a relatively simple version of this because all the charges are kind of lined up in a straight line. So you've got these three charges on the x-axis, and we'll go ahead and draw this picture out. Q1 is located at x equals 0. Q2, a little bit further down, is at x is equal to 0.3 meters, and then Q3 is at x is equal to 0.5 meters. So about there. And if you want to label each one of these, we have the Q1, which is -8 microcoulombs. The Q2 is +3 microcoulombs, and the Q3 is equal to -4 microcoulombs. So we want to figure out the net force on charge 3 due to the other two charges. So we're going to figure out what is the force on charge 3 due to this charge right next to it, but then we're also going to figure out what is the force on charge 3 due to this charge down here. You act as if this charge in the middle isn't even there and just say what is the net force between these two charges. So the way this is represented is the force has two subscripts on it. So the first one I'm going to do is F, and the subscript is 3, 1. What that means is this is the force on charge 3 due to charge 1. So I'm figuring out what is the force on this charge due to this charge. And then after that, I want to figure out what is the force on charge 3 due to charge 2. The force on this charge due to this charge. So this is all in part A. So we're going to use Coulomb's law, which is K. And then for the force between the two outside charges, it's Q1 and Q3 we're looking at, divided by the R, which is the distance between those two charges. So that's represented with the same subscripts, although in this case, that 3, 1 just represents what is the distance between charge 3 and charge 1. And then remember, it's Coulomb's law, which is squared. So if you plug in the numbers, K is the constant, 9 times 10 to the 9th. Q1 and Q3 are the 8 micros 10 to the minus 6 and 4 times 10 to the micros negative 6. Remember, you never plug in the negative signs in this equation. You only plug in the magnitudes and figure out the directions later. And divided by the R31, which is the distance between these two charges, which is 0.5, and that's squared, and that gives you an answer of 1.15 newtons. Now let's figure out what's the direction of the force on this charge due to charge 1. Well, charge 3 is negative, and charge 1 is negative, so because they're both negative, they're going to push away from each other, which means Q3 is going to be pushed toward the right. So next to this, we can say it's 1.15 newtons to the right. The other one is going to be the force on charge 3 due to charge 2 is K. The two charges this time are Q2 and Q3, divided by R32 squared. So the K is 9 times 10 to the 9th. The Q2 and Q3 are 3 times 10 to the negative 6 and 4 times 10 to the negative 6. And the distance between these, since this charge is at 0.3 and this charge is at 0.5, the distance between them is 0.2. So that's what we're plugging in, 0.2 squared. And that will give you an answer of 2.70 newtons. What's the direction in that case? Well, since Q2 is positive and Q3 is negative, those two are going to want to pull toward each other, so that means Q3 is going to go toward the left. So we can just write down the left after that. Combined, what do these do? F31 was 1.15 newtons to the right. F32 was 2.70 newtons to the left. The one on the left wins because it's bigger, so the overall net force is going to be to the left. And the magnitude of that force, since they're in opposite directions, we can just subtract them. If they were in the same directions, we would just add them. So subtracting 2.7 minus 1.15, the net force on charge 3, and I'm not going to put any other subscripts this time because this is the total force on charge 3, is equal to, subtracting them gives 1.55 newtons, and we said the one on the left wins, so the overall net force is going to be to the left. For part B, where could you place a fourth charge, which is negative 5 microcoulombs, so that the net force on Q3 would be 0? Well, we know, as of right now, the net force is to the left. So if we want to place another charge in there, we want the force due to that charge to be to the right to cancel out this overall force to the left. Since it's a negative charge, if you put the negative charge over on this side, over here, the negative and the negative, they're opposites, they would push away from each other. That would push Q3 to the left, which we don't want. We said we want to cancel out this left part, so we want to push Q3 to the right. So we actually need to put that Q4 somewhere to the left of Q3. Could be in this region, could be in this region, could be in this region, we don't know. As long as it's somewhere to the left. But let's figure out exactly where. So we're going to take the same equations we've been looking at, but this time we want to rearrange it for the R. And because we're talking about charges 3 and 4, we're going to change these subscripts to the 3 and 4. So R, 3, 4, that's the distance between charge 3 and charge 4, is equal to, and that's going to be K, Q3, Q4 over F34, and then since the R is squared, that means to get R by itself, you'd have to square rootify it. Plugging in all these numbers, 9 times 10 to the 9th, Q3 is 4 times 10 to the negative 6, Q4 is 5 times 10 to the negative 6, the F34, remember we want this force to cancel out the total net force we had over here, so the F34 is going to be the same as this right here, the 1.55 newtons. When you plug all that in, you get an answer equal to 0.34 meters. So it's 0.34 meters to the left of Q3. So to get a more specific answer, since Q3 is located at 0.5, 0.34 to the left of that would put you at X is equal to 0.16 meters. So it's actually located somewhere in this region. That's where the Q4 would be, and that X equals 0.16 meters is your final answer.